Hello everyone! In this video, I'll explain the basics of fluorescence spectroscopy using the energy diagram. We'll see how a molecule absorbs the light, what happens to the energy inside the molecule, and how the molecule emits light as a fluorescence. I'll also quickly recover internal conversion, intersystem crossing, phosphorescence, and quenching. To really understand the theory behind fluorescence spectroscopy, we need to understand the energy diagram that explains how a molecule absorbs light and how it can release energy, sometimes as a light. So to really understand how fluorescence spectroscopy works, you need to understand each component of this Jablonski diagram, or also we call it energy diagram. So let's start from the bottom and then slowly go to top. So as you see here on the bottom, we have S0. This S0 is, we call it ground electronic state. So this S0 is ground electronic state. So majority of molecules, they are in a ground electronic state. They stay there before we apply some type of energy, in our case a light. So they stay here. So once we apply a light, once we give the energy, the electrons within the molecule, then they start getting excited. They apply the energy, and then when they get excited, they jump from a ground state all the way to the excited states. So here you see this S1 and S2, they are excited singlet electronic state. So I'm gonna go ahead and write this is excited singlet electronic state. So I'm just gonna point an arrow. So as you see here, so we have 1, we have 2, and S3, S4, and etc. It goes up and up. So right on the right off, you see here this T1. So this is excited triplet electronic state, or also called excited triplet state. So, and I will explain how this T1 works and how it's different from S1. So I'm just going to say excited triplet state. Okay, so when we apply a light to, or energy to a molecule, it goes from S0 to S1 or sometimes S2, and then after some time it releases the energy or light, and it comes back to the ground state. So as you see on these small lines, each of these states, like the excited singlet state, the triplet state, or the ground state, each they have this ladder-like levels, and this is we called vibrational levels. This is the electronic state, and this is the vibrational state, or vibrational level. So we can say this is V0, and this is V1, and this is V2, V3. So these are all vibrational levels. So as you see, each of these states have their own vibrational states. So again, so when we apply the light to the molecule, it goes to the excited level, and shortly after it comes back to the ground level. It releases the energy, E is equal to h nu, and then when we apply again, it gains this E is equal to h nu. So this is how, this is more like a general definition for Jablonski diagram. As you may have heard, the fluorescence is emission-based spectroscopy. So let's take a quick look what happens when molecule absorbs the light. As I just mentioned, the molecules are typically on the ground state. So when we apply the light, it goes to the excited state. So let's imagine that we're giving exactly same energy to excite the molecule exactly from S0 to the lowest level of excited state. So the lowest vibrational level of S1. So let's just imagine what happens. So when we apply this certain energy as a light, so it's h nu, and then it goes there. So, and shortly after a nanosecond, so it typically stays in a S1 in a nanosecond, and that's what we call fluorescence lifetime. Fluorescence lifetime is when molecule absorbs before it releases or emits the light or energy. When it stays that shortly in excited states, that's what we refer as a fluorescence lifetime, and it's typically in a nanosecond. So shortly after a nanosecond, the molecule starts releasing the energy as a sort of light, and that's what you see actually a molecule shining under microscope, or the intensity where it's the emission. So remember, fluorescence is it's emission-based spectroscopy. You only see the molecule fluorescing only when there is a emission. So this is more like an ideal case. But however, it's not the actual fluorescence. We may not be able to get exactly the molecule from S0 to S1 to the lower ground level. So what happens when we excite the molecule, and then molecule can go from S1, S0 to somewhere right here on the highest vibrational level of the excited state. So in that case, the molecule does not directly go from S1, the higher vibrational level, to the S0 emitting light. So what happens is molecule loses the energy. When it loses energy for the vibrational state, it starts following from here to here, and from here to here, and then from here to here. Well, we call it vibrational relaxation. So it's vibration, and it loses its energy as a heat during this vibrational relaxation, and you don't see any molecule on the microscope or any emission yet. It only happens, the emission only happens when molecule releases the energy as a heat and then comes all the way to the S1, the lowest vibrational level of this excited state, and then from here it goes to all the way to the ground level. And here you start seeing the fluorescence. So that's why typically the energy of the emission is lower than energy of the absorption. So, or the wavelengths of the emission is higher than wavelengths of the absorption. So that's why, well, on the graph, so you see the fluorescent, if you want to plot it in 2 dimensions, which is wavelengths and then emission, I just write EM. So that's why you see the absorption right here and then emission right here. Why? Because the wavelengths of the emitted light is longer than the wavelengths of the excited light. And remember, this is the energy. So energy, the higher the energy, lower the wavelengths. Lower the wavelengths is the higher the energy. So that's why you see here, this is absorption and this is emission or fluorescence. So you may ask, so well, what happens when the molecule, when we excite, when it goes all the way to S2, not S1, not in the vibrational level of S1, but somewhere in S2. So I'm gonna redraw it. So here I draw more clearly what happens when the molecule, when we apply the energy and then molecule goes from S0 or electrons goes to S0 all the way to S2. So in that scenario, first you will see the molecule is undergoing again the vibrational relaxation, where there is no any heat and there is no any light, and it only releases the energy in terms of heat, and then it goes from S2 all the way to S1. So, and it's still not, and you don't see any light, you don't see any fluorescence or emission. And remember, I told you, so fluorescence only happens from the S1, from the ground vibrational state, to the ground vibrational state to the of excited state to the S0, and that's what we call Kasha's rule. But in this case, it first go from S2 to S1, and this this thing or this rule we call internal conversion. Internal conversion. When the excited state goes from the higher level, from S2 or S3 or S4 all the way to S1. So it first undergoes internal conversion, and then it will again lose the energy as a heat and goes all the way to the ground level or ground vibrational level of the excited state, and then it starts falling down, releasing the energy. So here now you see a light. Here, from here, no light. From here to here, no light, only internal conversion. From here to right here, still there is no light. There is a vibrational relaxation, and only the fluorescing, only the emission occur from the ground level of the vibrational state, level of the excited states. And then you see here the fluorescing, and that's what we call Kasha's rule. So there is one more path that electron can take to go from S1 to S0. So, and I'm going to explain what is that path and then how it's different from the normal regular fluorescence. So sometimes when we excite the molecule, I'm just going to draw right here again. When we excite the molecule, let's see until here, it goes again, it goes to the ground level of the excited states, and instead of emitting, it may go from S1 to T1. So we go from S1 all the way to T1. So this is what we call intersystem crossing. Intersystem crossing. Instead of going down and emitting fluorescence, some molecules, some electrons may take a different path. So what happens during intersystem crossing? During intersystem crossing, we call it, it's a spin forbidden. The spin of the electron changes, and you have probably seen it in general chemistry or organic chemistry. What's the difference between singlet and triplet? In the normal singlet, in normal occasion, so you see when there is the electrons go from S0, when they go to S1, that happens when this electron goes to S1, the spin doesn't change. Spin is pointing down here, and when we're excited, the spin doesn't change. But from triplet, what happens is from triplet, from this, it may go to this. Actually, spin changes. So changing spin, we call it, it's forbidden. It's not allowed. So that's why it's not a probable. There is less probability that will go from S1 to T1. But it happens. In that case, what happens is then molecule go from, or electrons go from T1, from triplet state, all the way to the ground state, like this. It goes to the ground state, and we don't call it fluorescence or emission, but what we call it phosphorescence. It goes to phosphorescence. So this is the difference between fluorescence and phosphorescence. Is during fluorescence, the molecule goes from a ground state to the excited state, and then it releases from excited singlet state to the ground state, releasing light or energy as form of light. But in phosphorescence, the electron goes from ground state to the excited state, to the singlet excited state. Then from singlet excited state, it goes to a triplet state, and then from triplet state, it goes down to the ground state, and that's what we call a phosphorescence. So this is the basic visual explanation of a Jablonski diagram and how fluorescence, how molecule absorbs the light and then emits it.